And I will turn it right over to Magdalena Kedziorek, who will speak about algebraic models for rational equivariant commutative ring spectra.
Thank you. So thank you for the invitation to speak at this conference. Thank you all for coming. I'm going to talk about commutativity in the equivariant world and how much of it we can still see when we do rationalization and look in algebra. So let's start with the commutativity. So that's going to be the first part of my talk. Because we need to set some things straight. We need to say what we mean. So, commutativity. So let's first take a look at the non-equivariant setting, when we all know what happens. So let me just record those things. So I'm going to be working in topological spaces or spectra. And by this I mean some nice model of spectra when I have a symmetric monoidal product. All my operands that I'm going to mention in this non-equivariant part are going to be in topological spaces. So we have some things we can consider. We can consider commutative algebras, and by this we mean the algebras for the operand comm. So operand comm, the terminal operand, a point everywhere. But when we're really interested at homotopy level of information, we might consider the infinity algebras. So those are going to be commutative, associative, up to all coherent higher homotopies. And those algebras are going to be algebras for some operand O, where O is infinity. So let me just briefly recall what that means. So that means it's a collection of spaces where I have a free sigma n action on the nth space, and it's every of those spaces contractible. So first of all, examples of infinity operands. Well, we know some examples. We can take the one that I'm going to work with. So the linear isometries operand. So for some infinite dimensional vector space U, we can take the little disk operand. We can take many more, but those are examples of infinity. Another example to get an infinity operand would be to do a cofibrant replacement of comm in the Berger-Mordijk model structure on topological operands. Not every infinity is going to be such a commutative, such a cofibrant replacement, but if you have a cofibrant replacement, it's going to be infinity. So they do exist. So now we can take a look at algebras for those operands. And let's start with spectra, since we really are interested in a stable world. So there's a theorem, which I'm not entirely sure who to attribute it to, but I would say maybe Thomason, which says that if I'm in spectra, and if I take O and O prime to be infinity operands, then O algebras are equivalent to O prime algebras. So it's really, I have one homotopical level of information in spectra. But there is a more interesting theorem, namely, and this is going to be May and EKMM. I know, I should, like, May is here as well, but just to give him more credit. In spectra, when you take a look at COM algebras, this is going to be...
He may be watching.
So now that we know that the homotopy type, or actually the whole story does not depend on the choice of the infinity, I'm going to just put the generic A infinity here. So the commutative algebras in spectra are going to be cool and equivalent to A infinity algebras. And if you think about it for a moment, it might be a little bit surprising because not true in spaces. So in topological spaces, if I consider commutative algebras are going to be products of Eilenberg-MacLane spaces, and in infinity algebras, group-like, are the infinite loop spaces. So what really happens in spectra? I mean, the key thing which goes into here, and that I'm going to just point that out because that's a hidden equivariant topology coming in the non-equivariant setting, is that if you take X in spectra, which is nice, then if you do the the n smash power of X, this guy, the action, the permutation action of sigma n is free on this guy. So homotopy orbits are going to be the same as orbits. And this is clearly not true in spaces. I mean, I'm going to have a diagonal which is going to be fixed. But in here, there's no diagonal. Something weird already is happening, and this somehow has to do with this group actions. So I think this talk is going to have many surprises in it. I'm going to try to point them out to you. There might be many surprises to you, but also to me as well. So we'll see how it's going to go. Yeah, but that's pretty much the non-equivariant story. So the upshot of this little introduction is that in spectra, all levels of commutativity, like homotopical levels of commutativity that you can think of, they pretty much agree. They model the same kinds of algebras. So let's take a look what happens in equivariant world. So that's going to be number 2. So what's the equivariant story? Well, the equivariant story is very interesting. So let's say we're working with compact Lie group. If something that I say doesn't work for compact Lie, assume it's finite. It's definitely going to work in there. So the setup. So I was previously saying we're working with topological spaces or spectra. Here we're going to work with G topological spaces or G spectra. And again, I need some nice model where I have a symmetric monoidal product, smash product. So I'm going to work with orthogonal indexed on a complete G universe, if you want a detail. So that's the thing, that's the setup. Our operands that we're going to consider now are going to live in G topological spaces. So we definitely have a similar start as before. We can consider commutative algebras in either G topological spaces or G spectra. And this is going to be just algebras for the operand COM. But this time, COM lives secretly in operands in G-top. So again, the terminal one, nothing actually changes. But now, when I take a look at infinity algebras, well, what do I mean? I can mean many things. So let me just put it out here. We have choices. So the first thing that we can do, it's not always a bad thing, we can ignore G. So by this one I mean we can take E infinity operad in topological spaces and give it a trivial action. So we're going to consider it as an operad in G topological spaces, but the action of G is trivial. Well, the good thing is that it forgets down to the E infinity operad to itself. But the work, so let me just point out that this would be the same thing as getting a same homotopical information as getting a cofibrant, same as cofibrant replacement in this model structure of Berger-Mordijk that I mentioned before for operads in G topological spaces. That would give me the same kind of information at the homotopy level, but somehow that's not the right thing to do. So the work of, and I don't know how to pronounce their names, so if they're like Constantinople and Wehner, they were working on infinite loop spaces equivariantly. And they figure out that, well, this is not somehow a good replacement for COM. There is a lot more structure that this thing doesn't capture, and I'm going to come back to this. But what they did, they figured out that instead of doing this particular thing, what you can do, you can take, so I'm going to put it here, take an operad, which is a linear isometries operad on a complete G universe. This is going to forget down to E infinity operad, but this one is going to have a property that the nth space is the universal space for G cross sigma n bundles G equivariantly. And they somehow show that this is a better thing to do. This is a better replacement for COM. And then, so this is ignoring G. This is taking as much G equivariance as possible, while still remaining E infinity underlying, which means sigma n3 at every level. So this is the minimal situation, this is the maximal situation. And then came Blumberg and Hill, and they said we can do stuff in between. Okay, so they came up with the theory of n infinity operads, and I'm gonna go over there. so there's no good name. So the trivial E infinity, I think we all agree what it means. This one, the genuine commutative, I mean the word genuine is not used enough in equivariant homotopy theory, so we might call it genuine. I think some people call it complete, but yeah, those are different choices. I might use either. Okay, so let's go back to the n infinity operands. So the definition, this is Blomberg-Hill, is that an n infinity operand is an operand O in G topological spaces which has two properties. So first, the sigma n action on On is free. And the second, that the level n, so maybe I should do it this way, so the n space is a universal space for a family, of subgroups F and O. So this is a family of subgroups of G cross sigma n. Which contains all subgroups of the form H cross 1 for all H subgroups of G. So if you stare at this definition, both of those examples satisfy the definition. If I take a non-equivariant operand and promote it to the equivariant world, this is going to correspond exactly to this minimal family that I have to have in my as the family for the universal space at the level n. If I take a look at this one, this has a maximal family, which we're going to discuss in a minute. If I add any other subgroup to this family, I'm going to destroy the first condition. Yep.
What do you mean by universal space?
Yes, this is a very good question. I was thinking about actually saying this. So if F is a family, then EF is a universal space for the family. It's going to be characterized by a condition on fixed points. It's either going to be a point or it's going to be empty, depending if H is in the family or otherwise. So we already seen this operand, and I said that it's going to correspond to the most basic n infinity operand that I can get. And the notation for us, any operand like this is going to be denoted E infinity 1, because it's coming from the non-equivariant world. This one we're going to denote E infinity G. So so I've already said that there's many things in between. I mean, depending on the group, but there might be things in between. But before I get to some examples, more interesting examples than this ones, I might mention some examples or not. Those are the two things which we basically are most interested in. So in this talk, whenever I'm going to be referring to some commutativity, it's either going to be this one or the other one. I'm not going to be saying much about anything between. So let me say a couple more things. So right now we know that we have some definitions of n-infinity operands. We know that we have at least a couple of examples, and I mean couple. What we have to see, and I mean this was a remark that I've already made. If we take O, an n-infinity operand, that it forgets to E-infinity operand in topological spaces. But different n-infinity operands are going to carry different information. So to actually make that more precise, I'm going to define a weak equivalence of n-infinity operands, or actually a good notion of weak equivalence for G cross, I have no idea how to actually say this, G cross sigma n, oh, let's do it. Good notion of good notion of equivalence for G top operands. And this is going to be saying that F from O to O prime is a genuine equivalence. It's another good use of genuine. If at every level it is G cross sigma n equivalence in G cross sigma n top. And by this I mean if I take fixed points with respect to all subgroups, their equivalences. So for all gamma subgroups of G cross sigma n. And there is a result. Okay, it's time to erase. The result of Gutierrez and White, and also another group of people. Sorry?
Evan was just curious about the other people were maybe.
You're freaking me out. Like everybody is watching. Okay, where was I? Okay. Yes, we have a theorem of Gutierrez, White, and Pereira. So I think those two groups arrived at the same conclusion, that there is a model structure which is not surprising on G top operands with this weak equivalences. So this is the proposed definition of Bloomberg-Hill of how we should look at n-infinity operands. Okay, so we have this weak equivalences. We have the operands, and they're given by some families. There's a relationship between families. But what is a good remark to state is that the homotopy type of the operands, so homotopy type of n-infinity operands of n-infinity operand is determined by the collection, by the sequence of the families. So now I need a name. So I'm going to call those families, so the family at the level n, the operand is called O. That's going to be the sequence of the families for O. And the families, I mean the families which are coming in this. Oh, I gave it a name. Very good. Those families. So why is that? Well, it's not difficult to see, right? If at the level n, I'm after taking fixed points, I'm either empty or a point. There's not much that can go around. Two operands which are going to correspond to the same families are going to be equivalent. They might not be equivalent through one map, because there might not be a map, but they're definitely going to be equivalent through the zigzag of two maps, because I can form their product and project down to both of them. That's the usual trick of E infinity operands, not equivariantly. So now that we have those operands, we see that they're really determined by the families. We can ask, okay, so what about the algebras? And we have a theorem of, again, Blomberg and Hill in G spectra. So the theorem says that, well, if I have theorem is going to have two parts. If I have two, or even three, an infinity operands, which are weakly equivalent, then the algebras are Quillen equivalent. So that's great. That's like the first thing. The second thing is, if O is not equivalent to O prime, they're both n infinity operands, then our algebras are not going to be Quillen equivalent to O prime algebras. It's more, I mean, we know that every n infinity operand is encoding some norm maps, and the statement is really saying that if I have algebras for some operand O, then there are going to be some norm maps encoded at the homotopy level, homotopy groups of this algebra, and they're going to appear in one of those and not in the other. And the norm map information is the homotopy level information. So there's not going to be a situation like this. And the third part, which is
I mean, there's no Quillen equivalence which preserves the underlying.
yes, exactly.
What you're saying.
Yeah. The third statement that I wanted to mention is that if I take E infinity G algebras, so the ones for the linear isometries on the complete G universe, this is going to be Quillen equivalent to COM algebras. But since the family for E infinity G is not the same as the family for E infinity 1, well, the E infinity 1 algebras are not equivalent to COM algebras. Okay? So that's somehow we're recovering the situation that they're like forgetting the G action and taking non-equivariant equivalences is not going to remember all the things that we want to remember. So this cofibrant replacement that we might be interested in doing was not the right thing. And you might actually ask, how come this is happening in spectra, G spectra, but it didn't happen sort of earlier? Like, it didn't happen in topological spaces? Well, the answer is it did. And this is going back to the work of Constantinople and Wiener. So this work on infinite loop spaces equivariantly. And what they did, well, they were considering linear isometries for different universes. And they were considering algebras for linear isometries operate for different universes for your group G. And they were able to show that those give you infinite loop spaces. So infinite loop spaces. But if I started with U, those loop spaces admitted the loopings by G representations which were in U. So if I started with a trivial G G universe, I had just the loopings by trivial representations, but if I started with the complete G universe, I had all the loopings. Those loop spaces are not going to be equivalent. So this already happened. We've seen this. We kind of ignored it at some point, but okay. So I've talked about those examples already. So let me give you, I'm almost well on time, intuition. What happens here? Well, if you take a look at the families F and O, where O is the E infinity G, well, so the maximal families that I can have, those are going to be graph subgroups. So all graph subgroups. So those are subgroups, gamma in G cross sigma n, such that if I intersect gamma with the 1 cross sigma n, I'm supposed to get a trivial element. And such subgroups correspond to, so graph subgroups, I already said that, but this is a subgroup H of G together with the homomorphism from H to sigma n. And those ones, on the other hand, correspond to H actions on the n element sets. So I give an n element set an H action, and people call it H admissible sets. So all sets like this with various n's we call H admissible sets. If I collect all of them for all subgroups of G, they form a nice indexing system, and understanding of the n infinity operands can be done by understanding those admissible sets. So what I wanted to do, I wanted actually to show you, well, if you had a group G which was quite complicated, then you might have many things between the naive and the most genuine n infinity operand. But if your group was the favorite group of this audience, so C2, or make it CP, where P is a prime, this one is not very interesting. So let's see what are the n infinity operands that we can get for CP. So this is going to be like a little example. Well, okay. So how many trivial guys are going to have to be there? So all trivial sets for n element sets are going to be always admissible. But like, what actual interesting guys I can get? Well, up to the level p minus 1, I can't get anything. Well, I don't have an interesting CP action on n element set when n is less than p. So that means that at the level 0, 1, and so on, up to the level p minus 1, the structure of every n infinity operand is going to be given by those spaces for e infinity 1. At the level p, I'm making my choice here. So is CP admissible? If it is, then my operand is E infinity G, and from here onwards, this structure is the structure of E infinity G. So I take all possible admissible sets. If the answer is no, then I'm back to E infinity 1. There's nothing in between. And a little exercise for the audience to warm you up. So how about you figure out what are the possible n infinity operands for C4? I mean, not now, later on, of course, during the break. But it's a little amusing exercise. Related to this exercise is the realization that equivariantly, if I take a universe which is not complete, I need to twiggle this universe a little bit, but not always it's true that little disk operad and linear isometries operad are going to be equivalent. There might not be. Yeah, so another question. If I take different and infinity operads, are all of them realized as linear isometries for some universe or little disks for some universe? Not in general, but like let's do it for C4. Okay, so I started with the intuition. So what is actually happening here? So when at the level n, I'm having some h action, some n element set with h action, that's actually going to tell me that algebras for this operad are going to have a multiplication, commutative multiplication, when I'm indexing, so let's call this guy T. This is an n element set with some h action. I'm going to have a guy like this and the multiplication like this, which is commutative, where the G or an h action is going to come on R and on the indexing set at the same time. It's in the quote marks because you have to interpret it correctly, but that's basically what it is. So the basic level of commutativity tells you that you have all those ones, which are commutative. The more advanced levels of commutativity, so all the passage from the naive to the genuine, are going to tell you that you're going to allow things like this, which are going to be commutative. Okay, so now we're getting to the fun part. We're getting to part 2, algebraic models. So the first thing to notice is that we're giving algebraic models for rational G spectra. So G spectra, rationally, we're trying to find an abelian category for G, such that if I take differential objects in this abelian, graded abelian category, this is going to be Quillen equivalent through some zigzag of Quillen equivalences. This is conjecture of Greenlees that for any compact Lie group G, there is such AG, and so I'm saying this is graded abelian of injective dimension equal to the rank G. So it's not going to be too big, it's going to allow for some computations. I'm not going to tell you all about the stages of this conjecture, but I'm going to tell you that we're going to consider 2 cases, when G is finite and where G is SO2. Those are two cases that are done. They are done monoidally, so this zigzag of Quillen equivalences is monoidal, and I'm going to come back to it in a moment. How is that linked to these commutativity things that I was talking about? Well, it's maybe surprising to notice that after this rationalization, I still have different levels of commutativity. I didn't kill all those different norms. So, let me start with G finite. So what do we know for the G finite? So we know that rational spectra are symmetric monoidally Quillen equivalent to the product over conjugacy classes of subgroups of G of chain complexes of Q, W, G, H modules. So this is the Weil group, so the normalizer of H mod H. So at this homotopy level, I have to give some credit. So homotopy level, this is Greenlees May. They did the splitting. The work, the model categorical level was done, I think, first by Schwede-Shipley, then differently by Barnes. And then I came along and did it again, but there was a reason for it. This one is symmetric monoidal. So all the colon equivalences that are coming into the picture are symmetric monoidal, and we're going to use that in a minute. So if you stare at this picture, you know that you have different levels of commutativity on the left-hand side. By which I mean there are algebras for those non-equivalent and infinity operands on the left-hand side. So what do they correspond to in here? In here I have just one level of commutativity. Something is commutative or it's not. So maybe it's not surprising that we can show that the most naive version of commutativity coming from the left is modeled by the commutativity seen in algebra. So let me make a statement. So this is a theorem. This is Barnes, Greenlees, and me. And what we're saying is that infinity 1 algebras in G spectra rationally, so G is finite, are colon equivalent to commutative algebras in the algebraic model. And forgive me, but I'm going to call this algebraic model DAG, and I'm going to say DAG. So the idea of the proof is not surprising. Well, how are you going to attack something like this? Well, you pick E infinity 1 operand. You lift, in equivariant world, you lift model structures from the zigzag to E infinity 1 algebras. As soon as you're non-equivariant, which means as soon as you push your equivariance outside of your category G spectra, so as soon as you're, let's put it this way, non-equivariant, you change your operand to come, and then you go from there. So from there, non-equivariantly, com algebras in spectra, rational spectra are just com algebras in rational chain complexes. And this is the work of Richter-Shipley. So you stick some equivariance on the outside of this statement and you're done. So, of course, that sounds very easy. It wasn't as easy as I just presented it. The difficulty is sitting here to know that you can lift the model structures. And actually knowing that you can lift the model structures, well, that requires some analysis of fixed points. So what do I mean by this? Well, of course we know that we can lift the model structure to commutative algebras if we start from the usual positive stable model structure on G spectra. But what comes into the proof is that at some point I'm doing certain localizations of the categories of G spectra. And if I want to do a lift to the categories of O algebras in there, there is a compatibility condition between E and O. So this object that I'm localizing at and this opera that I'm looking at, they have to be compatible. And that's what compatible means. If they're compatible, that I can lift the model structure. What compatible means, I need to analyze the fixed points. Fixed points coming on one hand from E, because E is going to have some geometric isotropy, but this geometric isotropy has to play nicely with those families which are defining an infinity operator O. I'm not going to get into details of this one, but the upshot is so any E is infinity 1 compatible. So I didn't actually say you localize the positive stable model structure here. So you can always do this, but this requires some analysis of fixed points. Why fixed points? What is coming into this picture? So this is related to, well, I can take a sphere spectrum, which is a very nice commutative guy, so it's the most commutative as you can get, and I can localize it at something. So let's do the localization E tilde F. So let's take F to be a family of all proper subgroups of G. I can take this universal space for the family, I can map it down to the S node, and I can take a cofiber, which is usually called E tilde F. So this is going to have information about G fixed points. This is carrying information about all the others. So if I did this localization, so E tilde F is the localization of the sphere spectrum at E tilde F. So what level of commutativity I'm going to get? Well, it turns out that localization in general, take your E infinity G algebra and move it down to E infinity 1 algebra. Unless you know something more about the relationship between the object that you're localizing at and the operator O. So in this particular case, E tilde F is E infinity 1 only, and this was known already to McClure, and I think recently Hill-Hopkins gave some other examples of this localizations phenomenon. But what is happening here is I killed all the information for geometric fixed points for all the proper subgroups of G, and I kept the information, non-trivial information, for the G. So how do I prove that it's not going to be commutative? Well, suppose that it is. Then if I take a look at G commutative algebras in G spectra, we know that the restriction functor at the level of commutative algebras going to H spectra, some subgroup of G, has what Hill-Hopkins-Ravenel call the norm functor. So it has a left adjoint. So if I take a look at E tilde F in here, suppose that it is in here, then I can take a look at the norm of the restriction of the E tilde F going to E tilde F, and that's supposed to be a ring map. Well, but this is contractible, so this is contractible. So we get a contradiction. But now is the time to move into, no, it's not the time yet, okay? Now I need to say, we got the algebraic model for the E infinity 1 algebras, and I need to say that there's a development due to Christian Wimmer, who showed using actually different methods. Because as I was saying, localization kills your additional information, and localization was the first step you used to get the algebraic model. So using those methods, you're not going to get anything more than E1. But there's a theorem of Christian Wimmer, which I'm going to say state that E infinity G algebras are actually equivalent in an infinity categorical setting to, and I need to rephrase something. Okay, commutative algebras in the algebraic model are really the same as if I take the orbit category of G and I make it discrete, so I get rid of all the transfers. I can map it into commutative algebras in Q modules, and that is this guy. Chain complexes. So now what Christian did, he introduced back those guys, which are in the orbit category, for G, and he just said this. Again. And the proof goes through very different...
Magdalena, sorry,
yes.
one question. So this discrete to quotient by conjugation, so what?
Yeah. You have to quotient by conjugations. Very good, thank you. So this proof goes through completely different levels, completely different methods. It uses Lurie's, I would say, the lifting functor theorem, or the monadicity theorem for infinity categories. Basically, we're showing that the geometric fixed points functor for different ages is going to behave nicely at the infinity categorical level, so it's going to lift to commutative algebras, and at that level is going to be an equivalence of infinity categories. Okay, so now I have 5 minutes. I can tell you roughly what's going on with SO2. So, we have an algebraic model for SO2. So this is the theorem of Greenlees, Shipley. But also Barnes, Greenlees, me, and Shipley. And again, why did we do it again? Because that gives symmetric monoidal equivalence. So right now I'm just going to state it as SO2 rational spectra are equivalent, and here I mean symmetric monoidally equivalent to the differential objects in the algebraic model for SO2. I'm going to probably tell you more about this guy in a second, but the similar result as before, since this is symmetric monoidal, and since actually E infinity 1 was compatible with any E for any G up there, I can do the lift with model structures, so I get another result. This is Barnes, Greenlees, me, saying that E infinity 1 algebras in SO2 spectra are equivalent to commutative algebras in this algebraic model. So again, that's maybe not surprising. That's again lifting model structures to algebras for certain operas. A little bit different techniques because that was just a different passage. But the idea is the same. So now, what do we do for more genuine commutativity? I mean, let me point out that the only two cases where we actually have symmetric monoidal algebraic model is the two cases that I'm just discussing right now, when G is finite and SO2. So this is the basis for discussing commutative objects in both sides. But what are the prospects for E infinity G in here? Well, let's take a look what we do when we do the passage. The first step in the finite case was to use the idempotent splitting, which was killing all the information of the norms. So we knew that there was no chance to get E infinity G at the finite set, at the finite group G. But what happens in here? Well, what happens in here, I'm not using the idempotent splitting. I don't have any idempotents for SO2. I could get them from finite groups, but that's not what I'm doing. What I'm doing is I'm doing the isotropy separation, or the Hasse square, or however you want to call it. So I'm presenting the sphere spectrum as the homotopy pullback of df plus e tilde f. So f is always the family of all proper subgroups, and def plus smash e tilde f. And it looks like splitting information. I mean, this guy is going to remember information about all finite subgroups. This one is going to remember information about SO2 only, and this one is going to tell me how to glue these two pieces of information together. So it looks like I actually split some pieces of information. But the surprise, surprise, this guy is commutative. So E tilde F for SO2 rationally is commutative. And this is a new work of Greenlees. So in fact, what happens there? Well, if I take a look at the norms, what are norms doing? They're jumping from a subgroup to a bigger subgroup if my index was finite. But then they're never going to jump from finite subgroups to SO2 because the index of all finite subgroups in SO2 is infinite. So technically there's no obstruction, and what John shows, he shows that it actually has a commutative model. There was no obstruction, and this one was realized. So if I do this, this whole diagram is actually happening in commutative algebras in G spectra or SO2 spectra. And now the real point, if you proceed to go to the algebraic model, what you're going to get at some point is you're going to get the t-fixed points of this gadget and taking homotopy groups. So let me just write it down. T is the SO2. So if I do this, I get a product, infinite product of QC in degree minus 2. So let's call them n, and let's do this product over n. So I get this huge product. So what I'm claiming now, and this is actually conjecture, soon to be a theorem, we hope, that E infinity G algebras in SO2 spectra rationally are going to correspond, and by this correspond, I might not put Colin equivalence, but I might need to put this this Wimmer kind of infinity categorical language. So I'm a very big fan of model categories, but that's where they might meet their limitations. But we actually conjecture that this is going to be equivalent to commutative algebras in the algebraic model. Plus extra structure, and this extra structure is going to be related to the structure that I'm going to put on this guy. So if I hit this guy with all possible idempotents and I split the information, there's going to be information for C1, information for C2, C3, and so on. And this guy is going to look like this everywhere. In the algebraic model, what I'm going to get a module over this thing, so I can again hit it with idempotents. And I'm claiming that the extra structure is going to be, well, not here. It's going to come from maps, which are going to be ring maps, well, leaving over this identity maps of QC, which are going to be the maps basically linking subgroups whenever the index of whenever the smaller one is a subgroup of a bigger one. So whenever you expect to have a norm, there's going to be something, a leftover of a norm. So this is a conjecture. We hope to prove it soon. Thank you.
Questions? Yeah.
So, I know that this is not quite right. It looks kind of like you're getting the norms are inducing maps from one geometric fixed point object to another. Is that?
It's almost so it's like you mean here or you mean for the finite group? What was exactly for the finite group?
Finite group.
Yeah, for the finite group is definitely true. Yeah, so you're going to have a ring map between geometric fixed points, basically. In here, those are not like the algebraic model for the which is corresponding for the finite subgroup is not really the geometric fixed point at this subgroup. It's something more complicated. It's like Borel cohomology of something. So once you take those maps and you restrict to the finite subgroup, that's what you're going to recover. You're going to get a map between the geometric fixed points.
I'm super confused by the fact that this E twiddle F is going to be commutative. I mean, like, the underlying spectrum is 0, right? Like, I mean, can you elaborate on the fact why this is commutative and what this means?
So E twiggle F.
I mean, this E for actual proper subgroups F. So the thing in the upper right of the diagram, right?
You mean this one?
Yes.
So this one is going to have geometric T fixed points, SO2 fixed points.
Yes.
So the way you prove that it's going to be commutative, you look at the endomorphism of this guy. You don't look at the whole endomorphism operand on this guy, but you look at the whatever is living over. So okay, this endomorphism operand is going to go to the endomorphism operand of S0. So in there, I'm going to have at the level 0, at the level 1, I'm going to have an identity map. Let's call it iota. I can take a look what's the pre-image of this identity map. So let's call it D of E tilde F. And you're showing that this guy is going to have actually structure of E infinity G operand. It's going to act on your E tilde F. So
No concept that the underlying spectrum is contractible. You cannot move from the trivial group to S1.
Because that's what I was saying. The norm map is not jumping the high, right? The norm map is only the index.
That's no contradiction, but it's super weird. The underlying spectrum is 0. All fixed points for proper subgroups are 0, and
it is. So it is actually true that
like
for higher tori, if you do the same kind of trick, if you take a cofamily, so this is a space, the universal space for some cofamily. If your cofamily is closed under taking finite index subgroups, then your guy is going to be commutative.
So this just means the actual fixed points, I mean the SO2 fixed points are commutative, or what? I mean,
yes.
In practice, if I give you like some of these weird guys and make it genuine like commutative, you just give me a written structure on the actual fixed points.
And
the same as geometric fixed points.
Yeah, the geometric fixed points.
Okay, one more? No? Okay. Okay, we'll save further discussion for later as usual. And let's thank Magdalena one last time.